to keep. But textbooks that were in my area of expertise where I knew I'd use, like chemistry, physics, mathematics, especially advanced mathematics, and my engineering books, I kept them and I wrote in them. I've got tons of notes that I still reference today. I would recommend, even though a lot of you don't see yourself using any of this now, you're going to take an examination called the Fundamentals in Engineering examination, the FE exam. Does everybody follow me? Now, some of you are going to go on to get a professional license that allows you to do a lot of things, make a lot of money, but there's liabilities involved too. And you will be referencing material that we cover in this book, probably for the professional engineering and the FE exam. But more than that, especially if you're a general contractor or you're in a small company, you'll find yourself going back again and again to textbook materials. I know Google's out there. I use it extensively, but a lot of the stuff, I still look at the things that I know where they're at, and I remember all the tricks. I'm just level with you. So if you can get a physical copy, I'd recommend it. I know in this day and age with ebooks, maybe you like electronic copies and you make notations there. I don't do that very often, but I understand that. I'm just saying keep good notes because you may find yourself accessing them in the future. And I hate to say this in a negative way, but sometimes the availability of easy electronic stuff like PDFs makes it real easy to lose too. And I've had that happen. I don't know if you've ever had that happen, but I've lost entire files. I don't know what happened to you. Okay, enough of that. Now, I gave you a bunch of problems, and typically when I come into class, and this is a huge class, what people do is they have some questions about a problem. Now, I just put up the solutions, so obviously you didn't have time. You didn't even have the solutions, I don't think. All right, but I put up the solutions to the problems I gave you. Something else I'll say, I don't know what's available out there. Usually, if I don't have a solutions manual to a course I'm teaching, I make a general request to the student body and they'll supply me one. They have access to anything out there easier than I do. So I assume somebody in this room probably has access to them, and you have GroupMe that I'm not part of, don't you? Does everybody have access to the GroupMe? Or who created that? Somebody created it, it wasn't you. Didn't you say somebody else created it?
Someone else created it, yeah.
Do you know who created it? When the person remained unknown for obvious reasons. Anyway, GroupMe is your best friend in my opinion. If you don't know something, ask. People are very good at helping out. I found out desperate people help desperate people, stuff like that. All right, so any problems you want me to do, we're going to do a few, one way or the other, but I would prefer doing something that you have an interest in rather than me just picking one. Anybody, how many tried it? I recommend you never get behind the notes. You may, I know this time you didn't have the solutions, it was a little, or the answers, it was a little, why am I doing this? I don't know what I'm doing. But by the same token, at least you should have to get an idea of the type of problems and how to go about doing it. So anybody, go ahead, sir.
Can you go over 116 and 119?
Yeah, for 116, I don't know it by heart, so let me just look and I may ask you to tell me the problem. 116. Okay, now this is one of those things that's about power, and it's all about signage and sign convention. So what they have in 116 is they show you something. It's just, this is what they show you. I wish it was a little clearer. These are brand new markers, by the way. Just to show you the code and stuff. Anyway, they show you a block. That block doesn't mean anything. It's some kind of an electrical device. Doesn't tell you what it is. Then they show you a line here, and they put another block, but it doesn't tell you what it is. However, it gives you polarity and direction of current and voltage. Please listen to this. Can you all hear me in the back and see this? In the back, if for whatever reason you can't read, let me know immediately. All right, for this one they have an arrow this way, and then they have I is equal to minus 6 amps. Now I want to make sure I show this one, and please be attentive here. And then they show a voltage plus or minus here, and a voltage V. And then they show the power associated with this is equal to minus 24 watts. And determine the unknown voltages and then outward. Okay, I'm going to do the first part. Can everybody see this okay? Now here's a trick on this one. It's not really a trick. This is my suggestion to you. Can everybody see that negative sign there? That means the current is going the wrong way, in my opinion. Just change the direction of the current. Got it? That's all that negative sign means. If it's negative 6 that way, it's positive 6 that way. You all with me, class? So let's do it. So really, that current, this again, is a brand new marker. Stop. If I didn't know better, I think somebody's on a prank on me. So really, this is the direction of current. Can you all see that? It's going from left to right. Okay? Now, they're asking for this unknown voltage, but they give you the power. And I like to circle the negative signs on all my work simply because my handwriting's horrible and I make scratches sometimes. So I circle the negative signs so I don't mistake them for just a scratch. That's my personal way of doing business. If money's involved or it's serious. What does minus 24 tell you about the power associated with that element? Anyone? Supply, right? Y'all grip me on that? Now, I could go through this a lot of different ways. I'm going to show you, but I consider the most reasonable way. If power is supplied, and I'm going to break this out over here so I can talk about it directly. And I know I have a current I equals 6 amps going that way. I have a current I equals 6 amps coming out of that device. Do you all follow me? I'm just breaking it out from anything else. Now, that minus 24 tells me the current has to be leaving the positive terminal. Do you all follow me on this? How many do? It has to be leaving if it's minus 24 watts because it's a supply. It's supplying power. If the current was entering the positive terminal, it would be dissipating power and would be considered positive. You follow me on this? It's just a standard. So that means the actual voltage here, without being negative, in other words, I'm trying to show you the positive sense voltage would be this polarity. Now I'm just showing you. You all with me? And you understand the reasons, right? How many do? Anybody not? Do you not understand that? No, not you, behind you. I mean, if you don't, ask. Because if you don't ask, I can't help. And there's no, you can't be embarrassed here. I mean, you just ask. Because sometimes there's subtleties that I don't know are occurring when I'm talking. I mean, something I might have misspoke, stuff like this. Now, how do you get that actual voltage? We know that what? The 6 amps, I times V, technically the way that would be, we can do it right here, but I'm going to walk over there and do it. If I look at this, I have a positive voltage here, so it's V, and the current is entering that, right? So it would be times I, because the power is always, you take the positive terminal, and the current entering it, you get, this is how we get the voltage. And we know that's equal to what? Minus 24. You can do it this way, but I like doing it that way. So I've got a voltage here, an unknown voltage, and a current of 6. Now it's a positive 6 amps, and it's minus 24 watts, right? So that means what? V is equal to what? Minus 24 over 6, correct? Or minus 4 volts. Y'all with me? Can everybody see that? I hope I'm answering your question. Try to be as clear as I can about this. What it really means is this voltage is minus 4. So the real voltage, the way I like to say it, if we were talking plus to minus, this would be 4 volts. And the minus to plus just has to do, this is an easy way to think about it. If you had a meter, you take the ground or negative terminal of the meter or lead of the meter and you put it on the negative terminal of the voltage, and then the positive terminal on the positive, you'll read a positive voltage. You all with me, class? How many have ever measured the voltage on a car battery? On a DC, say a 1.5 volt battery, on any battery. What do you know? If you get the leads wrong, it's negative, right? That's the one thing you keep reminding yourself. It's that simple. Y'all follow me on this one? How many understand this? Good. Do you have another question? Or somebody else had a question? Yeah.
We do 225.
Yes. Absolutely. This is a brand new reverse. I hope this works. All right, problem 225. How many have books here, physical books like this one? Anybody? I get one, George. I'm just saying. You don't have to, but I would. All right. This is good. So this is problem 225. And here we got 12 milliamp source current. Then you have 4K. K ohms, and then you have 2K ohms. And then you have 2K this way. And you have 1K. And they want this voltage right here. And they want this current flowing right here. Now first, I want to make sure everybody can see. Can you see in the back? All right, far back, everybody? Okay, for this one, they give you a current of 12 milliamps right here. Now, I assume everybody knows what these prefixes mean, but some don't. K is 1,000. How many knew that? K ohms, right? And K just means 1,000. Milli, or M for short there, is 10 to the minus third, or 1/1000. Does everybody follow me on that? You have to be familiar with that. You're engineers. You probably have had this all the time. You've had it since the time you were in physics. Now, when we take a look at a problem like this, we can go through every aspect of it fairly easily, and I'm going to do that. The first thing I'm going to do is this. I'm going to talk about something called current division. I didn't do current division or voltage division last time. This is a perfect problem to introduce it. These concepts, you don't have to use these, but they make life easier. So with current division, better yet, let me do voltage division first. What it really says is this: if we have a voltage source here, plus to minus some voltage, Vs, and we have just two resistors in series. So I'm going to say I have some R1 here and some R2 here, and I'll get out of your way, and you want this voltage across the second resistor. Just write this down. It's a simple series circuit. Two resistors in series with a voltage source, and I want the voltage on one of them. Y'all with me? Okay? Now, I know that these two are in series. So the net effect of that would be a resistor of just R1 plus R2. How many know that? So I'm not. Does anybody not understand that? If they're in series, you add up the resistors. How do you tell if they're in series? The same current must flow through both of them. You all follow me? So R1 plus R2 would be the net resistance. That means the current flowing here, which will be the same since they're in series, would just be this voltage Vs over R1 plus R2. Do you agree with that? What is that law called that I'm using? V equals IR or any form of it? Ohm's law, right? You'll use that extensively. It's very easy. Now, if that's the current flow through there, what do you know about voltage across the resistor? Same current through both of them, right? What's the voltage across V2? It would be that current times R2, wouldn't it, class? So I can say this voltage V2 is really going to be this current, which is Vs over R1 plus R2 times R2. Or now we talk about voltage division, which becomes obvious. If you have a source voltage, or you know the voltage between two resistors, and you want the voltage just across one of them, you can say the voltage across the unknown resistor, in this case, it's going to be V2. V2 is just going to be equal to a ratio of R2 over R1 plus R2 times the actual voltage Vs. This is voltage division in its simplest sense. And it doesn't matter how many other resistors are in series with R2. If you add all those up and just create a new single resistance, it's just R2 over the sum of all the series resistances. Y'all with me? How many understand that concept? It's very simple, right? Next, we're going to do current division. The current division is basically the same. Go ahead, ask it. Don't worry.
I was going to ask, why is there R1 on one of them and R2 on the other one?
What
in the
is it?
numerator.
What?
Is that R2 on the bottom?
Here, this is R1 plus R2.
Yeah,
this is
the
R2.
numerator. The numerator.
That's R2.
Oh, okay.
That's my handwriting.
Yes, sir.
I'll get better, I hope. Just yell at me, really. I mean, don't worry. My handwriting has never been good, and it's only gotten worse. So, I went to a Catholic school. Anybody else went to a Catholic school? Do you remember penmanship? That's the one class I've flunked so many times. Anyway, that's a joke, but I think I passed. Anyway, that's how you do voltage division. Now for current division. All right, now this is the simplest thing with current division. Just watch. I'm going to create a current source, not a voltage source. A source is something that the known value of voltage or current is part of. It's defining it. So we're going to assume that this has a current IS. We don't know what the voltage is, we know the current. Y'all with me? Now if you have two resistors in parallel, make this R1 and make this R2, and I want the current through R2. We'll call it I2. They're in parallel, correct, class? How do you know they're in parallel? What's the catch? What's the giveaway? Anyone? That's profound. What is it? Same voltage, right? Series, same current through both. Parallel, same voltage across both. Got that, everyone? All right, so now let's find this voltage across them. What is this voltage going to be? I'll call it Vs. How would you get it? Think about it. I'm asking everybody. Don't answer yet, just think. Well, I got two parallel resistors. Can I get a single equivalent resistance? Anyone? How many think so? You're right. It would be what? 1 over R1 plus 1 over R2, or if you have just two, this is a nice formula to remember. I can say the equivalent of these two, R12 is equal to 1 over R1 plus 1 over R2, or I can say R12 is simply equal to, and the way a lot of people do it, they're going to multiply top and bottom by R1, R2, and then they get R1, R2 over R1 plus R2. Can you all follow me on this? Either one is identical. You see that? But it's only good for 2. So now I'm going to say, well, this is the same thing as having a current IS and a single resistor here. And the single resistor here has the value R12, and that's equal to R1 times R2 over R1 plus R2. Can everybody follow me? I'm just replacing the 2 with 1. Everybody? All right, now what's the voltage across those? We got the current, we got the resistance, right? What's this voltage going to be? It's just IS, right, times that. R1, R2 over R1 plus R2. Do you all agree with that, class? I'm just showing you, it's obvious, but take a look. You good with that? All right, now, what would the current be through any one of those? If I wanted the current right here, I know the voltage is right here, Vs, right? So what is I2 going to be? And I'm going to take a second. Ask yourself this question logically. If I have the voltage, I do, and I have the resistance, I take the voltage divided by the resistance, right? With me? What is it going to be? Well, there's the voltage. So I'm going to just write it down. IS, right? Then it's divided by R1 plus R2, right? Then it's got to be multiplied by R1, R2. That's the actual voltage. Now I have to divide that by R2, right? Everybody agree with that? How many see the R2s on top and bottom cancel? Let me move that thing out of your way. I'm sorry. Y'all with me? So what's it going to be? Simply just IS, right? And it's going to be R1 over R1 plus R2. Now the simple way to think about that is that if you have resistors in parallel, the smallest resistor will have the largest current. And if you have resistors in series, the smallest resistor will have the smallest voltage. The largest resistor will have the largest voltage. You with me, class? All right, now, how many looked at that problem? Not many, but these are important problems that set the stage for the next lecture because they make you think about it first, okay? All right, we got through this. Any other questions before I move on? It's good to do this. Anything at all? All right. So the next thing I'm going to talk about, now we talk about resistors in series and parallel, right? There's one other type of phenomenon, it's called delta Y networks. And I'm going to talk about this, then we're going to go through some problems and apply some of these things and talk about Kirchhoff's voltage and Kirchhoff's current law being applied to problems. This is not really tricky, but it can drive you nuts if you're not careful. I wanted to ask this, do you have any kind of a course in what you're legally liable for, like business law or anything in engineering? You get business econ, don't you? How many do? I thought you did. Didn't you get business economics as a requirement or not?
We did like an engineering economics.
Engineering economics, do they cover what you're legally liable for?
I'm really not sure.
Anybody know? No? It's okay. I'm not sure that's a good idea. It's not in this day and age. All right, now, just write this down. I want you to listen because you're going to read it in the book and get scared. All right, this is called a delta to Y transform with resistors. What it means is this. If I have a network of just 3 resistors, regardless of how it's hooked up to the circuit, if I have some resistor, call it R1, another resistor, R2, and then a resistor here, R3, this is called a delta formation. Now, typically they're going to put a point A, B, and C. Now, those points A, B, and C are connected to a much larger circuit, all right? But this is just a cutout of that. This can be made equivalent to, and if you have A here, C here, and B here, what a lot of times, and this is something with the power company we'll get into later, is very common. They can make this equivalent to resistors RA right here, and they put a little ground there. Then RB here, I'm sorry, RC, and then an RB here, and they ground this, and that ground means 0 volts. Can you all follow me? So that would be a Y configuration. It's upside down, it's a Y. Y'all with me, class? Yes, sir.
You use RA, RB, and RC. On the other one, you use R1, R2, and R3. Are they comparable?
We're going to show you the exact equivalence. We're going to show you what RA, RB, and RC are in terms of R1, 2, and 3. That's the whole idea. As a matter of fact, a lot of times what they'll do is put R delta 1, R delta 2, R delta 3. That way it's very clear the designation and what it is assigned to. And this would be RAY, RBY, and RCY. Y'all with me? Okay, now, if we have that, and you know that these 2 points electrically have a resistance between them. Do you agree with that, class? If you measure the resistance between here and here, you would have this resistance in parallel with these 2 in series. Do you all see that? Remember, nothing else is connected. If you want to measure the resistance between here and here, you would say that the equivalent RAC would be equal to R1. Now look here, this is important. The sign for being in parallel is just 2 parallel lines. R1 in parallel with R2 plus R3. Can you all follow me on that? Likewise, if I come over here and I look at RAC or RCA, they are the same. RAC from this perspective would just be what? RA plus RC. Can everybody see that? All right, this is not connected, right? I hope it's not a student. You just won the lottery. Sure. You guys get these annoying phone calls? I never used to get this. It happens. I mean, I'm getting it from everybody. Politics, my car insurance expired, this, that. The Elks Club's calling me. I don't care. Anyway, I don't know how they get my number, but somebody's giving it out, and I'm very suspicious. All right, so what is this going to be? It's just equal to what? RA plus RC. Correct, class? You with me? Now, usually, either these values are known and we want these values, or these values are known and we want these values. You all with me? But this is a very common transform that's necessary to do analysis in general. Now, I'm going to tell you, we could write, now just look at this, we have 3 unknowns on either side. How many equations are we going to need to get a unique solution? 3. Y'all with me? At the end of the day, they're in the book, I'm not going to make you responsible for knowing the general way to do this, but I'm going to show you a specific way you have to know, all right? Just hear me out before I'm go. At the end of the day, if you write all 3 equations here, and all 3 equations here, and then you do a solution so you find RA in terms of R1, 2, and 3, what happens is, and this, I don't know what page it says in the book, so let me give it to you in the book so you can see it, and I'll show you how easy it is. Yeah, these are, this is on page 35 at the bottom. He shows you delta to y transforms. And he shows RA, and he does it right. At the end of the day, when you all do it, and I'll just tell you the secret. RA, now that's the RA over there, is equal to R1 plus R2 over R1 plus R2 plus R3. We can solve them simultaneously, but he's got the same labeling as I do. Sorry, he does, but my bad. I'm sorry. This is times. My bad on this one. This is times. Does anybody have the book available to you right now that you can look on or not? Anybody at all? It's there. He does use the R1, R2. You see it? Okay. Now, I want to tell you something. People start getting nervous. That looks like I can mess that up real easy. I'm not going to hold you responsible for that. You got me? Here's what you got to know. In this one, it's when the resistors are equal in either of these configurations, and you have to go to the other one. So this is what I'm going to hold you responsible for. I can draw it a different way. So if you have a delta configuration, and it doesn't matter its orientation, I'll call it R delta, and R delta, and we'll call it A, B, and C. And you want to go to a Y configuration. I'll even put it this way. Make that A, B, and C, ground that. And these are all RY. This one is going to be easy to see. These are all R deltas. That looks like an A. And those are all RY. Can you all see it in the back? Far back? You good? All right. So look, from here to here, we have this, right, in parallel with these two in series. Can everybody see that? Current must flow this way, right? Current must flow this way. Therefore, the voltage between here and here must be the same, right? You agree with that? So if I look at this, I have R delta. It's in parallel with really 2R delta, isn't it? You agree with that? It's just 2 times R delta. Everybody see that? Follow me in the back, guys? How many do? Just, I'm trying to get a read on this class. Anybody not see it? Can you see it? Here you got R delta. It's in parallel with these two in series. Each one of them is R delta. Same identical value. Got me, class? What's that equal to? Over here, when I go from A to B, I get 2RY, don't I? Can you see that? How many can see that? This one's not connected, doesn't count. So that has to be equal to 2RY. Now if we have our delta and we want our Y, this is a typical kind of thing you're going to see with power. There's more to this, but that's what you typically see. Well, these two are in parallel. Do you remember before I could take one and multiply it by the other? Over the sum of the two. Do you all remember that, class? So here I can take this times this, and I get 2R delta squared over 3R delta. Can you all see that? Everybody with me on that? Can you with me on what I'm doing? I'm taking these two, this times this over this plus that, and that's equal to 2RY. So from that, I can deduce that RY is simply what? Now look, you see how one of these R deltas cancel that one? And it's really going to be what? R delta over 3. So it means if if these were all, say, 30 ohms resistors, and I wanted to create an equivalent, identically equivalent system, only with a Y configuration, these would be 30 over 3 or 10 ohms apiece. You all with me, class? And the two would be electrically identical. The nice thing about a Y configuration is you've got a ground there, which becomes very important later, especially for measurements and safety reasons. You with me? This does not have a ground involved in it. And the power company, might as well throw this out there. When they distribute power, have you heard of three-phase power? Three-phase power means they have three different voltage points with respect to a ground, and they're all 120 degrees out of phase with the same magnitude. And they can distribute this is something we were talking about, transformers, where the transformers or the power lines are in a delta configuration, or they can be in a Y configuration. Identical voltages and everything like that. The difference is in the actual phasing and the magnitude of the voltages. I mean, identical forms of the voltage in terms of 60 hertz and a large magnitude. But that comes later, I just want to mention it. Okay, now for problems. We're going to do Kirchhoff's current law and Kirchhoff's voltage law problems to set the stage for this, before we get into nodal analysis. So I gave you some problems to do. I'm picking one right now, and I think this thing will be a pretty good problem to showcase stuff. We're going to use, first I want to see how you'll do it as a class. Be attentive here, because there's a quiz coming up, right? This is Wednesday and Friday. You all hear me on that? There's a quiz coming up on Friday, so be here and be prepared. There'll probably be 5 or 6 different types of quizzes that are handed out, so you can't, there'll be no, I mean, basically everybody will get a unique quiz relative to your neighbors. Go ahead.
So why did you say equal to 2R1?
Can anybody answer him? Why is this 2RY? That's a good question. I'm going from here to here, right? Do you see that? Is this one connected electrically? Can any current flow here? Get rid of it. Now do you see it? That's all it is. If I don't connect the other one to some place, it's not connected, no current can flow there, it's a dead link. Just ignore it. Make sense? You got me on that one? All right. Back to this thing. Let's go ahead through some problems. And I personally feel the only real way to learn a lot of physics, mathematics, engineering in general is working a lot of problems. The things you don't know become clear, and your questions are answered by doing problems. That's my opinion. Some people will argue with me. It's understanding what the formula means. Well, I don't know. I don't understand what the formula means until I try to use it. Anyway, so I'm going to do problem 223. If you got another one to do or want me to do, just let me know. And we'll even do problem 226 after that. Didn't I assign 226 or didn't I? How many did 226? It's a nice problem. It's easy, but it requires some thought. Okay, so 223 first. And this is a straightforward one. Here, he's got a current going down here. I equals 12 milliamps. And then you have 4K. I'm going to show you a trick with this one. Now, a lot of times I don't put ohms after it. I just put the K symbol. It's implied if it's a squiggly line like that, it's ohms. Got that, everyone? Then they have 4K, 12K, and 6K. And they're asking for this current in this direction. Can everybody see this, class, in the back? It's not a hard problem. I'm going to suggest something. When I look at this, all right, I know they want the current that way. But you see how the current's going down that way? It's coming into, this is called a node right here. If you have more than one path for current to come in and out of, an electrical connection that has the same voltage, it's called a node. You might as well call that node 1 right there, the whole bottom part. You all follow me on that, class? Just a bunch of copper wire. Well, I know that the current, the actual positive current's going that way. So I'm going to do a little something that makes my life easy. I'm just going to say I want this current, and I'll call it I1 prime, and I'll make it negative at the end of the day. You all follow me? I'm going to see this. Now, if I asked you to calculate that current, there's a lot of ways to do it. Let me just label a few, and then I'll tell you the way we're going to do it. I could do what? I could find one single value resistance. I have 6 in parallel with 12. That's 4K, 4K, and 4K is 2K, right? 2K times 12 milliamps is, or what, 24 millivolts? It would be plus or minus 24 millivolts. Then I could divide that by 4K and get the current. You all with me? That's one way. Don't worry if you didn't follow everything I said. It's just deduction. Another way is what? Well, I could take 12K and 6K, and I find out the parallel combination is 4K, and then I could use current division, couldn't I? I could say that this current right here would be that current, which is 12 milliamps, right? Times the opposite resistance, which is 4K, over the sum of the two, which is 8K, and it would be simply 12 divided by 2. Wouldn't it, class? How many understand the logic now? I know I'm talking fast. Either one of those does it. You could use current division. You could find a single voltage and divide that voltage by the resistance. So there are a number of ways to get the same answer. Probably the one they're looking for you to do is say, let's take these two resistances and replace them by 1 and use current division. Can you all hear me back there? So what is the value of that? Well, I could take 1 over 12 plus 1 over 6, right? So it's 1 over 12 plus 2 over 12 is 3 over 12. Flip that, I get 12K divided by 3 or 4K. Do you agree with that? Now, you play around with it. You get good at this till you do it enough times. But you got calculators if you're really struggling. So, this is 4K. Now, if I want this and I'm priming it too, can you all see that I've got a total current going into that parallel combination of 12 milliamps? Do you all see that? In the back? That current, if I want this current, I'd say that current times what? The opposite resistance, 4K, over the sum of the two, which is 8K, would be this current, right? It would be exactly half, 6 amps, 6 milliamps, right? This would be 6 milliamps. Now, anytime you have parallel resistors, they have to have the same current through them. So if you wanted to just take one look at 4K in parallel with 4K, you got 12 milliamps coming in to both. You got exactly 6 milliamps going through both. You all with me, class? That's the rationale. Mathematically, it's sound. That's it. But the final thing is that's the current going this way. The actual current they wanted was this, wasn't it, class? So that would be minus what? 6 milliamps. Do you agree with that, class? Because they want the current in the other direction, which is legitimate too. Everybody hear me on this? You understand? Now, the last thing I'm going to talk about is problem 226. And this problem, in my opinion, just causes you to think and get familiar with the types of situations you run into. Now, I had to do this one time. I was asked a specific question about, did it matter if the resistor was horizontal or vertically oriented or on a diagonal? It makes no difference in the world what the topology looks like in terms of its orientation. The only thing that matters is the electrical connections between the points. That'll become clear to you. Here, they do this. They want the resistance between terminal A and terminal B. And here they got 2K. And then they have 10K. And that's a K. And then they have 8K. And then they have 3K coming straight down. And then they have on this diagonal here, 6K. And it looks like that. Can everybody see this, class? And if you can, if you could possibly bring something so you can view a copy of the text and the problems, it would probably be helpful, especially if you're taking notes. I mean, she's got a tablet of some sort, and so do you. And I see a lot of other people with them. A lot of my students have these things where they can literally take notes on the tablet and save them. I recommend you do this. You can literally expand a problem and put the solution right there. Now, if you look at this for a second, I'm going to ask you to think about it, but how would you solve this? If I would just want the resistance between terminals A and B, a single equivalent value, what would you do first? Anybody? You see what you can combine. Follow me? See what's in parallel, see what's in series, and keep reducing it. What do you notice about the 6K and the 3K just by looking? Class? How many see they're in parallel? The same voltage. It doesn't matter if one's tilted this way. It has no bearing on the situation. Electrically speaking, that point would be, consider that blue, consider this red. Anything between blue and red would be in parallel. You all follow me? So I could replace them by what? 2K, right? So now I have 2K. What's next? Anyone? Work with me. Go ahead, say it. I see the 8 and the 2 is? And replace it with 10. You're right. Don't go again yet. Let them write it down. Think for a second, not you, somebody else. You got a Michigan cap on, you're a little lost, huh? I went to Penn State, I'm gonna get you. Okay. Anyway, are you ready? You don't understand the joke until you live where I live. Anyway, it's really Ohio State, your enemy, not me. Coming back to that, what's next? It's a football season, I gotta make a football joke. Go ahead.
The 2 10s are in parallel. So
Hear 'em?
that's
2 10s are 5, right? Yes, they're 5. And finally, 5 and 2 in series is 7. Y'all follow me? How many see that? They probably had to do that in physics. I don't know what they asked. These are not difficult, but here's the problem. All this is assumed you know very well. So when you get into the next stuff, if you have any weaknesses, you'll just crush yourself. So please do the problems. See you Friday for a quiz into class. This is packed to the gills, so come early.
I might actually